Hi everyone. So today in this video we're going to learn about how to calculate the isoelectric point of cysteine. So in our previous videos we already learned how to calculate the isoelectric point of glycine and then a triprotic amino acid as well of aspartate. So we did calculate the isoelectric point of those two amino acids, and today we're going to calculate the isoelectric point of cysteine and then lysine. So let us see how do we do it. So as we already know what is pK1, pK1 is the particular pH where the carboxylic acid of the amino group will lose its hydrogen. pK2 is the value where the alpha amino group will lose its hydrogen, and then pKr is that particular pH in which the side chain will lose its hydrogen, right? So as you can see the structure of amino acid over here, we have the alpha carboxylic acid and then we have the alpha amino group, and then the side chain could also have any of the groups which could donate hydrogen. It could have a carboxylic acid as it was in terms of aspartate, or it could have an amino group that we'll study in this lysine. So we'll just move forward and then we'll try to see. Okay, so first let us make the structure of cysteine. So how does a cysteine structure look like? So it's very simple. I'm just going to take yellow. So I'm going to make the backbone of amino acid. So this is the backbone of amino acid. Now we'll have to add the R group. So in the R group, we have SH. So what exactly is this SH? This is actually the thiol group. So this is the structure of cysteine. Cysteine is also written as CYS, which is the 3-letter code, and C, which is the 1-letter code. So now we have made the structure of cysteine as well. So now let us try to understand how do we calculate the isoelectric point of cysteine. So I'm just gonna make it small. So out here we are given the pKr value, pK1 value, pK2 value, and then pKr value. So as we all know that this first structure is the structure where the hydrogen ions are very much high in number. That means this is actually the structure, when the amino acid is present in a very acidic solution, and we are moving forward to the basic solution. So this is acidic, and then we are moving towards little bit acidic, then more basic, then most basic, so that kind of thing. So out here the hydrogen ions would be very high in number, right? Because the solution is acidic in nature. So what will happen if an amino acid is present in an acidic solution is it will accept one hydrogen ion. That means it will undergo protonation. So which particular group will undergo protonation? Because this already has an H, this already has an H, there could be a possibility that this could gain one hydrogen ion. So this is going to gain one hydrogen ion, and then it's going to become 3, and then it's going to gain a positive charge. I'm going to draw it with the pink so it's going to gain a positive charge, right? So now the charge of this particular molecule will be +1, right? This is going to be +1. So let us move to another one. So as we move forward, the solution is getting less acidic. That means the concentration of hydrogen will be this. In this one, the concentration of hydrogen was very much. So I'm just going to put more arrows. And in this one, the concentration of hydrogen is gonna decrease a bit. So I'm going to put 3 arrows. So here we have 4 arrows, and then we have here 3 arrows. So I'm saying that the hydrogen concentration is getting less. So now what will happen is, this was already 3, and then this had gained a positive charge, right? Now when the solution was very much acidic in nature, during that time the amino group of the amino acid gained a positive charge. But then when the hydrogen ion is getting decreased and the solution is becoming less acidic, and it will reach a particular pH of 1.70, now what will happen is the pK1 value will be seen. How? So this particular COOH, when it reaches this particular amino acid, when it reaches this 1.71 value, now the COOH will lose one hydrogen. So it is losing one hydrogen. After it loses hydrogen, it will have a negative charge, right? So can I say that the net charge of this particular molecule, this molecule is 0, right? So this molecule is actually called as the Zwitter ion, right? This is actually the Zwitter ion. Now let us move forward. As we are moving forward, we can see that the solution is becoming less and less acidic and more basic. So in the third one, now we already have NH3 over here, and it has gained a positive charge. This already lost its hydrogen, and then it has a negative charge. Now which value will come first? Is it pK2 or pKr? pK2 value will come first, right? So pK2 value is associated with which one? This one, right? So it is associated with this one, because this is the pK1 value and this is the pK2 value, and pKr value is this one. So please follow up with me. So now what will happen is, as the solution is getting more and more basic, now the first pH that the amino acid will reach is pKr value. That means this value. So when it reaches 8.33, what will happen is, this thiol group will lose its hydrogen. So now what will be the net charge of this particular molecule? It will be -1, right? And what is the concentration of the hydrogen ion? The hydrogen ion was very much higher in the first one, a little bit less in the second one. Now it has decreased. So only 2 arrows. I'm showing only 2 arrows because out here we have 3 arrows, right? So hydrogen ion are getting less in number. Now let us move forward to the last one, that is the last one. So now we already have a COOH which has lost its hydrogen ion. We already have a thiol group which has also lost its hydrogen ion. And then now what will happen is, the pK2 value will be there. Now it will reach the pK2 value, right? After it reaches the pK2 value, this molecule, after it reaches pK2 value, now what will happen is, pK2 value is associated with the amino group of the amino acid. So this NH3, after it reaches 10.78 pH, now it will also lose its hydrogen ion. Now what will be the net charge of this particular molecule? Because this NH2 has lost its hydrogen, extra hydrogen, and it has lost its positive charge as well. So this is going to be minus, minus, -2, right? And then the concentration of hydrogen ion has decreased. Actually, like I should have drawn like this, but just to show you, guys, I have written it like 4 arrows, 3 arrows, and then 2 arrows, and then 1 arrow. So please follow up with me. Okay, so we understood how to calculate the isoelectric, the how to draw the isoelectric pkr, pk2, pk1 value, right? So we are going to calculate now what is the isoelectric point of cysteine. So as we know that whenever we talk about isoelectric point, we're going to take the two charges which are right and left to the Zwitter ion. So out here the Zwitter ion is this one, right? The Zwitter ion is this one because this is carrying a 0 charge. Now we're going to take this value, we're going to take this value, and then we are going to take this value which is next to the Zwitter ion. So which values are this? This one is the pk1 value, right? And then this one is the pkr value, right? So let us take this value. So (1.71) plus we have 8.33, right? So I'm just gonna like zoom it. 1.71 plus we have 8.33. So I'm just gonna calculate it. So that will be 10.04 divided by 2, which will give 5.02, right? So this is the isoelectric point of cysteine. So now let us go to another one, that is lysine. So let us first understand the structure of lysine. So lysine, as you can see, lysine has a very long chain, and then lysine has 4 carbons which is attached to the amino group. So now I'm just gonna show you. So this is the alpha carbon, right? This is the alpha carbon of lysine. This is the beta carbon. This is the gamma. This is the delta. And then this is the epsilon. So we can say that lysine can be named as epsilon amino acid. Can we say that? Yes, we can say that, right? Because the epsilon group is attached to the amino group. Okay. Now let us see how can we calculate the isoelectric point of lysine. So I've drawn this. Okay. So as we know that, oh my god, as we know that this is the pk1 value, this is the pk2, and then this is the pkr value, right? So when the pH is below this particular thing, what will happen is this amino group will receive a hydrogen and it will gain a positive charge, right? So it will gain a positive charge. So now what is the total charge of this molecule? It's plus 2, right? Okay. So now when this particular molecule will reach 2.18, it is the pK1 value. So COOH will lose its hydrogen, right? So we all know that, of course. So I'm just gonna copy paste this. I'm not gonna draw it. Okay, so we have it out here. So the amino group has already gained a positive charge. Now is the turn of the alpha carbon to lose its hydrogen. It's going to lose its hydrogen and it's going to gain a negative charge, right? So what is the charge of this molecule now? This is going to be 0 or 1. What do you think? This is going to be +1, right? Because this and this will cancel each other, and then this positive charge will come here. Okay, so now let us see what will happen when we move towards the other, towards the higher pH. So now lysine is moving towards the higher pH. As soon as it reaches 8.95, it will be the pK2 value. That means this amino group will lose its hydrogen ion, right? Because pK2 is associated with the alpha amino group, which is attached to the alpha carbon. So let us just paste it, and then we'll see. Okay, so what will happen now? As I said that this particular amino group will now lose its hydrogen. So after it has lost its hydrogen, it will be 2, right? Okay, so what is the okay, let me make this one also. I almost forgot it. Okay, so what will be the net charge of this molecule now? This will be 0. Right? Okay, so now when we are moving forward, and then this particular amino acid reached this pH. Now what will happen is this amino group will lose its hydrogen, right? Because this is the pKr group, right? I hope you're not getting confused. I've just drawn this like this so that this is carbon 1, this is carbon 2, carbon 3, carbon 4, and then this is alpha, beta, gamma, delta, epsilon, which is attached to this NH3, right? So now let us come back to the pKr value. Okay, so now what will happen is this okay, so now what will happen is, as I told you, that this is going to lose its hydrogen, right? This is going to lose its hydrogen. So when it is losing its hydrogen, what will be the net charge? This will have 2. I'm gonna write it with pink because pink. Okay, so this is gonna be 2, right? Okay, so this is gonna be 2. So now what is the net charge? It is -1, right? So which molecules am I going to take for the calculation of the pi of lysine? I'm going to take this. This is the zwitter ion, right? Because it has a 0 charge, net charge 0. I'm going to take this one, and then I'm going to take this one. So what is the pK value? It is 8.95 and 10.5. So let us just see 8.95 8.95 8.95 plus 10.5. So there is we have to take the average of these two values. So when I take the average, it's gonna be 8.95 plus 10.5 divided by 2, which will give us 9.725, right? Oh, this is 5. So approximately like 9.7, 9.8, we can see that, right? So today we calculated the isoelectric point of cysteine, and then we also calculated the isoelectric point of lysine. So I hope you liked this video. If you did, please like, share and subscribe, and then thank you.